Hey folks, welcome to this episode on equilibrium expression calculations. So when we're looking at our equilibrium expression, recall that it's the concentration of products over the concentration of reactants. Now if we have this example over here, where we have A and B, we have the small a shows the coefficients of our balanced equation, same as the B, C, and D. Now when we bring it into this K equilibrium, remember it's the products over the reactants to the power of their coefficients in the balanced equation. So our C becomes our concentration to the power of its coefficient here. So if this coefficient was 2 in the balanced equation, we bring it to the power of 2. Now remember what this K equilibrium means. It looks at the ratio between the products and the reactants at equilibrium, therefore the K equilibrium. And remember that K equilibrium is just a generic expression. It could be Kc, Kp, Kw, etc. But what the main thing is that it always looks at the ratio between your products and your reactants. In this case, when we have a very, very small KEQ, that means that at equilibrium, there's more reactants than there are products. So even though this reaction is going back and forth, back and forth, back and forth, it mainly ended up producing or reproducing the original reactants. And so we have a greater concentration of reactants than we have of our products, giving us a very small KEQ. So this is what it would look like at equilibrium. A lot of reactants, small number of products. On the other hand, if our K equilibrium is large, we have a large amount of products and a small amount of reactants in our equilibrium state. If we have times 10 to the 10, that we can basically say that all the reactants have turned into products, the reaction has gone to completion. Same thing is true here if it's times 10 to the negative 10, we're going to say that the reaction barely even happened or didn't happen at all. So let's look at some questions that you might see in terms of our equilibrium expressions. So let's look at our first one. It says, when the following equilibrium system is analyzed, it's found to contain 0.0070 moles of nitrogen, 0.002 mole of chlorine, and 0.95 mole of NCl3 in a 5-liter flask. Calculate the equilibrium constant for this reaction. So it doesn't say Kp or Kc, so right now we're just going to say Keq and then go from there. So I'm going to write out my Keq constant. So we have Keq, and that's going to be equal to the concentration of our products over our reactants. Our products in this case is NCl3, and that's a gas, to the power of 2, which is its balanced coefficient, over we have N2 gas to the power of its coefficient. In this case, it's 1, there's no coefficient there, multiplied by Cl2 gas to the power of 3, because its coefficient is here. Now, what we have to make sure is that our K equilibrium expression is correct, because we can't include any solids or liquids. They're incompressible, and therefore they're not included. We only include gas or aqueous. And so far, we're good. So what we're going to do is we have to look at the concentration. These are square brackets. They represent concentration. We're just given mole. Mole of this, mole of this, mole of this. We need to figure out concentration. But one key part of that is that we are given volume. So we're going to take all of these moles and divide them by 5. So if we look at that, if we look at our mole of N2, it's going to be 0.0070 mole divided by 5.0 liters. And remember what equation we're using? Where C is equal to N over V, moles over volume. So in this case, when we look at N, we're going to get 1.4 times 10 to the negative 3 mole per liter. For Cl2, we're going to do the same thing, so 0.002 divided by 5 liters, and we're going to get 4.4 times 10 to the negative 4 mole per liter, and for NCl3, we're going to get 1.9 times 10 to the negative 1 molar. Okay, so here we have our concentration values. Now what we're going to do is we're just going to take these and sub them into our equation over here. So NCl3 is going to be 1.9 times 10 to the negative 1 mole per liter, so molar, and that's going to be to the power of 2, over our concentration for N is going to be 1.4 times 10 to the negative 3 molar, that's to the power of 1, multiplied by 4.4 times 10 to the negative 4 molar to the power of 3. So if we do all of this out, what we get is we get a final K equilibrium value of 3.0 times 10 to the 11. Now remember, K doesn't really require any units, so we're just going to leave it at that. That's a pretty big number. What that means is that, this equilibrium arrow has pretty much gone all the way to completion. We could pretty much get rid of this equilibrium arrow and just make this arrow go this way, because this is a big KEQ. Anything larger than 10 to the power of 10, we can say that it almost goes to completion, and so it's really gone, all this reactant has really turned into product. Let's look at another example here. It says when the following equilibrium system is analyzed, it's found to contain 0.25 mole of NH3 gas, 0.080 mole of hydrogen gas in a 3,500 milliliter flask. The equilibrium constant for this reaction is 5.81 times 10 to the 5. Calculate the moles of N2 at equilibrium. Okay, so in this case, they're actually giving us our rate. This is the equilibrium constant over here. They're giving moles here and moles here, but no concentration. Now remember, we can use our volume to figure out our concentration. Just remember that 3,500 milliliters is going to be equal to 3.500 liters. We can use that to figure out our concentration. So let's do that first. Let's take a look. Let's do our K equilibrium equation first. K equilibrium is going to be our products over reactants. So again, NH3 gas to the power of 2 over N2 gas multiplied by H2 gas, and that's to the power of 3. Let me just erase that to make it a little bit better. 3. Okay, let's look at our concentrations. So for NH3, we have 0.25 mole divided by 3.500 liters. And in this case, we get 7.143 times 10 to the negative 2 molar. For H2, we get 0.080 mole divided by 3.500 liter, and we get 2.286 times 10 to the negative 2 molar. Okay, so we have our concentrations. We are looking for 8 for N2, so we have everything that we need. So what we're going to do is we're going to rearrange our equation to solve for N2. Our N2 is over here. So what we could do, and we're going to manipulate this in a number of ways, we'll bring our terms at the bottom here all the way up here. So we're going to multiply both sides by these terms. So what we'll get is we'll get the concentration of N2. I'm just going to drop the states for now, just to make it a little bit easier to see. H2 to the power of 3 and KEQ, and that's going to be equal to the concentration of NH3 to the power of 2. So now we have this. Let's isolate for our N2. So the way that we do that is we get rid of these things over here. So we divide both sides by H2 to the power of 3 times K equilibrium, and we'll isolate for N2. So the concentration for N2 is going to be equal to the concentration of NH3 to the power of 2 over the concentration of H2 to the power of 3 times your K equilibrium. So if we sub in our values now, we have our concentrations for NH3 and H2. We have our K equilibrium value. So if we plug that in there, NH3 is going to be 7.143 times 10 to the negative 2 molar to the power of 2 divided by 2.286 times 10 to the negative 2 molar, and that's to the power of 3, multiplied by our K equilibrium, which is 581 times 10 to the 5. So if we do all this through, what we get is we get a number of, let's just bring that up over here, 7.4 times 10 to the negative 4 molar. Now, it's asking us for moles of N2. This is giving us molar. So in the same sense, what we're looking at is here, we need to do this. Remember that this molar is in mole per liter. We need to get it into just moles. So we need to multiply by liter. Remember that what our equation is, C is equal to N over V. N is equal to C times V. So our C is 7.4 times 10 to the negative 4 mole per liter. And we multiply by the liter. What is our liters? It's 3.500 liters. 3.500 liters. Our liters will cancel out, and we get 2.6 times 10 to the negative 3 mole of N2. All right, let's look at this example here. It says at 1500 degree Kelvin, the partial pressures of these compounds are as follows. So we're given all the partial pressures here. Now remember that K equilibrium is just a general term for Kc and also Kp and a whole bunch of other ones. So in this case, we're going to be looking for Kp specifically. Our Kp is going to be looking at our products over our reactants multiplied by their coefficients, or to the power of their coefficients. So here what we're going to look at, we're going to look at the partial pressure of CH3Cl to the power of 1, because the coefficient of the balanced equation 1, 1, 1, 1, multiplied by the partial pressure of HCl to the power of 1 over, this is going to be the partial pressure of CH4 to the power of 1, and the partial pressure of Cl2, again, to the power of 1. Now, just a note, this 1 over here, just get that erased, this 1 over here should be on the outside of our bracket, just right over there. Okie dokie. So we have our general equation set up. Let's just plug in our values, because everything is in partial pressures already. They're in atmospheres. So we're just going to put these in. Our CH3Cl is, if we look at this, 0.24 atm to the power of 1. We can just drop that. Multiplied by HCl, which is 0.47 atm, over our partial pressure for methane, which is 0.13 atm, and multiplied by our partial pressure for chlorine, which is 0.35 atm. All right, so after we get all this, our Kp is going to be 24.79. Okay, so we have two significant figures, so we'll just call that 25. So again, our K equilibrium is going to be pretty huge. This reaction is really going to go to our right and favor our products. Here's another example that we have. In this case, what we have is consider the above equilibrium equation. It says at 295 degrees Kelvin, the partial pressure of each gas is 0.265 atmospheres. Calculate the value for Kp and Kc for the reaction. Okay, so Kp, once again, is just going to be our equilibrium expression. So we have, if I look at our K equilibrium, that's our products over our reactants. So what we get is in this case, we're going to do Kp, so we're going to look at partial pressures. Our partial pressures is going to be our products over reactants. So in this case, our partial pressure of NH3 to the power of 1 multiplied by the partial pressure of H2S to the power of 1. Now, you might want to say divided by NH4HS. However, look at the state. The state says solid. So because it's solid, we don't actually include it in our equilibrium expression. So we're pretty easy here. We have our Kp equilibrium expression. We know that the partial pressure of each gas is 0.265, so that means that gas and this gas. So we simply plug those values in, 0.265 atm multiplied by 0.265 atm. Again, they're both about to the power of 1. But we can drop that, so our value is 0.0702. Okay, now this is our Kp. We figured that out, that's done. But now it's also asking us for Kc. So what is the relationship between Kp and Kc? Well, Kp is equal to Kc, R bracket RT to the power of delta N. Well, if this is the case, we can actually just swap these out. Both of these are equilibrium expressions. We can just do Kc is equal to Kp RT to the power of negative delta N. Okay, so when we switch out these two terms, the Kp and the Kc, our delta N becomes negative. So, first of all, let's figure out what our delta N is. Now remember, delta N is the sum of the coefficients of the products minus the sum of the coefficients of the reactants. Now in this case, there are no reactants because our reactants are not included in our equilibrium expression because it's a solid. So our sum of our coefficients, our delta N, is going to be the sum of the coefficients of the products. So of the products, we have 1 plus 1. Okay, and we subtract the coefficients of our reactants, which is 0. So what we get is 2. So our delta N is going to be 2. Now, in this case, we have to look at this unit to figure out what our R is going to be. Remember, R is our gas constant. It's either going to be in kilopascals or atmospheres. Because these values are in atmosphere, we're going to have to use the value for R for atmosphere. So the value for R in terms of atmospheres is 0.0821 atm. And that's liters times mole times Kelvin. Okay, there's our entire unit there. T is going to be equal to 295 Kelvin as stated in the equation. So let's put this all together. Kc is going to be equal to 0.0702 multiplied by 0.0821 ATM liters mole Kelvin multiplied by 295 Kelvin. So this multiplies first, and this is all going to be the power to -2. So if we do this all out, our Kc is going to be equal to 1.20 times 10 to the -4. So here's our Kc, and here is our Kp. So both less than 1. Now, if we have to do any kind of stoichiometry after we find our K equilibrium, we can do it this way. So if we, for example, have a reaction and we have to double this up, all we're going to do is we're going to take the square of it. So if we double it up, we're going to square the value of K. So this is going to be 8 squared, giving us 64. If we have to divide it by a certain number, so in this case, if we divide it by 2, we go, if you can see that we have 2, 1, 4, and this becomes 1.5 and 2. What we do is we do the opposite. If we square this, what we're going to do here is we're going to take the square root of this, and that's going to be equal to 4. Now, if we look at this and we have this order of operation, this is the equilibrium constant that it's being asked for. So we have SO2 plus NO2 gives us SO3 and NO. And this is kind of like Hess's law. We have our individual elementary steps, and we're going to cross things out. Now, if we look at this, we actually have NO2 where we need to be on the left side in the right proportion. We have NO on the right side in the right proportion. SO3, same thing, proportion. SO2, right side. So the only thing that we're seeing is that we have O2 that we're going to cancel out. And it works out well because they're on opposite sides of the arrow. We don't see it in the final reaction, so we can cancel those out, and it works perfectly. So when we look at this, when we add these two equations together, what we're going to do is we're going to take the product of their two K values. So in this case, when we add these two equations together, we're going to take 2.2 and multiply it by 4.0, giving us 8.8. So in summary here, if we have our value of K and we have to do a little bit of stoichiometry, if we multiply the stoichiometry by a value n, then we're going to change the equilibrium value, the K value by a power of n. If you do the reverse, you also take the inverse of the K. If you decrease the stoichiometry by n, for example, divide by n, we're going to take the square root of n. And finally, if you add the chemical equations together, we multiply or we take the product of the equilibrium K values of each other. So thanks very much for watching. See you soon.